Good afternoon. Thanks for coming to the talk. So, my name is Jason Lynch. I'm CEO of Equal One. Our company was founded about 6 years ago on a simple but quite controversial idea. So, I'm not sure if you've noticed over the last 2 days when companies have talked about quantum computers and put up graphics of what quantum computers are going to look like, what we've seen is massive facilities and massive infrastructure. There is a general view today that quantum is going to be big quantum. We're going to need massive rooms the size of maybe this conference room. We're going to need massive cooling. We're going to need, massive amounts of money to make these. The simple but controversial idea that our company was built on and we've been working on for the last almost 6 years is that quantum should look much more like what computing looks like today than anything else. That rather than start from the ground up, we should build on everything we've done to get where we are today, whether that be in generative AI or GPUs and all of the technology that we've built. So our view is that we should look at quantum processors that look like chips today. We should try to get them into compute that can fit into today's infrastructure. And that is the way that we will get to quantum commercial reality. So I'll tell you a little bit about the background of the company, the history of why this is now ready, and why today, and we're now coming out of that mode of researching and doing the science and starting to engage with commercial customers. So I'll talk a little bit about why there's momentum in this approach, what makes the approach scalable. I'll talk a little bit about silicon spin qubits, which is really the key to enabling quantum that looks much more like compute today than what the general consensus is. And then I'll talk about Equal One's innovation. We call it Unity Q. It's a chip that unifies the very latest classical compute with quantum compute on the same chip, monolithically integrated. So today, quantum really is about a race to a scalable qubit platform. So we're a hardware vendor, and like all the other hardware vendors, we have picked our qubit modality of choice, and we're busy trying to prove out that ours is the most scalable platform. So I've called out 5 platforms here today. There are more. These are, I believe, probably the most mainstream. You have superconducting, trapped ion, neutral atom, photonic, and silicon spin. And all of these have made massive progress, right? I think what we've heard over the last 2 days, is massive progress. And I think the industry continues to make technical milestones in each of these modalities. And I think that is needed, and that is going to prevent a so-called quantum winter, because each of the companies are making milestones and pushing progress forward. But there are challenges in each of these modalities. The challenge with superconducting is that it operates at 40 or 50 millikelvin. It's extremely difficult to put any other components at that temperature. Trapped ion and neutral atoms typically use lasers to drive, which means sometimes the gate speeds can be longer than superconducting. Photonic, yes, photons are a fantastic source of qubits, but we're still some ways away being able to do this monolithically. We think silicon spin is the best approach that combines not the best quality raw qubit metrics, but when you look at the system and what's capable with the overall system, we think silicon spin is the way to scale qubits and the way to get to commercial reality. So if we look back a little bit in history, this approach to quantum computation has been around quite some time. So 27 years ago, Daniel Loss and David DiVincenzo, two very well-known gurus in this area, came up with the proposal of using quantum dots as qubits. And that was 1997. You have a lot of groups around the world looking at that, trying to get it. The first experimental proof of that was done by Andrew Zurak's group in Australia in 2013, that proved that we could actually get a qubit with spin that would be the basis of a silicon spin qubit. So that was the first time that was demonstrated. And now, 10 years later, we're at a point where we're coming out of the research labs, we're integrating these spin qubits with other electronics, and really, this forms the core thesis of equal one. At every point in the road, classical computing has advanced through silicon. And at every point in the road, people have questioned whether it's possible. People have questioned whether Moore's law is going to end. People have questioned whether we've run out of road. And every single time, silicon CMOS has come up trumps. And it's our view that in quantum, the same will happen. Silicon CMOS will answer the questions of how to scale quantum. So really, the unlock comes from three pillars of innovation. The first is the qubits. So the qubits are based on a quantum dot, which is similar to a very small transistor. And the dimensions of that quantum dot are such that you isolate a single electron in the quantum dot in a specific energy state, and you're able to control the spin of that electron as your qubit. So you have a very small transistor, you isolate the electron, and you use the spin of the electron as your qubit. One of the material breakthroughs that has led to this is purification of silicon. So one of the reasons why this is sort of coming out now, and it's a little bit behind some of the other modalities, is that if you purify the top layer of silicon with a specific isotope of silicon on its own, you get 100x improvement in the qubit performance, which really unlocks performance that enables us to start to scale. So the types of numbers we're getting today, is around 10 microsecond coherence time, gate fidelities in the 99% for single gate, 98% for 2-qubit gate fidelities, which is at the number where you can start to work with it. You can start to think about error correction schemes. You can start to think about scaling. So you take those qubits, and because they're very similar to a transistor, you can put lots of electronics around them. And the other benefit of these qubits that enables integration is that they operate at a much warmer temperature. So they're typically called hot qubits. The temperature of operation is targeted around 1 Kelvin, and that gives us plenty of power to do all of the other electronics to control and error correct the qubits. And that then enables us to do a very small form factor. So we can fit everything, cryo cooler, all components that are required in a server rack-mounted form factor using Unity Q as the basis. So these are really the pillars that enable this innovation. So what you end up with is you end up with an entire quantum computing ecosystem, the measurement, the control, the readout, and the error correction all on one chip. And you compare that to the systems that we're used to, where you cannot do that, and you need to have a lot of external components in order to control the qubits. So this really unifies quantum and classical in one hybrid processor. So, we believe you're going to need very powerful classical resources very close to your quantum core. The idea of shipping data from one data center to the other in order to do your quantum calculation and then waiting till it comes back, to us, seems like we're not going to get very far in real-world applications. And you're really going to need an extremely high latency, tight coupling between that classical and quantum. So because it's done on a process that is similar to the process that goes into the processors in your smartphones, ultimately we can scale up to millions of these quantum dots. Now, we're not there yet. There's still significant challenges to get there, significant engineering challenges. But we can see a path very quickly to 1 million qubits on one single chip. And I guess that's the difference between our approach and some others. We started with a scalable, high-quality production process and have been working for 6 years to get the foundations going. Now we can scale relatively easily compared to other modalities who have started with the qubit and worried about scaling afterwards. We have the latest process geometries, which means we can use precise measurement and control of the electrons, and the purified silicon unlocks long coherence times so we can do quantum algorithms. We also have a very unique approach to error correction. We use AI on the chip, so we have a neural network right at the qubit array. We train that neural network to recognize the error signals in the qubits, and within tens of nanoseconds, we can correct the qubit error also. What that means is you can have real-time error correction. So as the data is flowing through, as the algorithmic data is flowing through, we can correct in real time so that to the user, this looks like real-time error correction. The other thing that you can do is use a lot of different error correction schemes, and you can also have adaptable qubit arrays. So let's say your fidelity for your algorithmic qubit needed to be 99.99%. You could have a certain number of logical qubits, but you could change that actually in real time. You could change that if you needed a lower fidelity, you could get more logical qubits. So this approach enables the user to fit the logical qubits to the algorithm. We have the current version of this chip in our lab right now. It has, we believe, the first ARM core at 1 Kelvin. We're testing that right now, and we're hoping to make an announcement on that later this year. It has integrated neural networks and memory on the chip, and it massively simplifies the development of algorithms, and it's on a standard foundry process. As I mentioned, because of the work we've done and because of where we are with the technology, we're now starting to engage commercially with customers, and we're talking about our first units that will ship early next year. And these will be rack mounted. Again, I know there's a number of quantum computing companies that have rack mounted systems, but typically, they are still quite large. Ours literally fits in a 22U cabinet initially, getting smaller, and is fully self-contained, needs no special environment. We could actually have it up here on the stage, plugged in and operational. It needs no special environment. We're starting with 6 qubits in early 2025. If anybody's interested in ordering one, please see me after the talk. We're taking orders right now, and we'd be delighted to talk to you. So in terms of why we think this is the right approach, it's a scalable approach that will scale to millions of qubits on chip. We put that onto QSOC, quantum system on chip, which enables efficiency, performance, and precision. very low cost of ownership. So because we're built on standard existing supply chains, we can build this for a very different price point than other quantum computers. And part of the reason we took this approach is that it's our belief that quantum computing should not just be for the richest companies or the richest countries. Quantum computing should be used to level the playing field rather than make the rich richer, and so we see sort of democratizing quantum computing. We want to enable millions of developers on this, and so this is a very reasonable price point, I would say, as compared to some other quantum computing prices. UnityQ transforms software development because what you're doing is you're coding an ARM core, or similar to you doing an FPGA. You've got the quantum resource right there, and you're not worried about latency and bandwidth. And it enables on-premise quantum, which actually is we're seeing a lot of interest, right? So many companies interested have their own private data center, their own air-gapped data centers, where they don't necessarily want to send data to the cloud because it's too sensitive. If you're doing a new drug, if you're looking at new materials, if you're doing a financial application, there's many times you will not want, nor you may not even be able to send your data to the cloud. So the fact that we can put these machines into data centers in early 2025 is something that's getting customers really excited about. And then just to maybe illustrate the concept again, because we've talked about this for a number of years, and actually it doesn't quite get across. So this, as many of you will know, is NVIDIA's latest chip, and we know that's been built on the foundations of the semiconductor industry and now has billions of transistors on board. And this really is a marvel. And again, our view would be, why would we tear all of that up and start again? We need to build on top of that, and rather than having new infrastructure, new manufacturing processes, we should leverage what's available and tightly couple a quantum core to that existing compute rather than starting anew. So the company is headquartered in Europe, in Ireland. We have offices in Delft, in Canada, in Silicon Valley. We have a very strong quantum team, 50 patents, 40 Nature papers, a lot of publications. Like I say, we've been working on this technology for 6 years, making sure that this is scalable and this is the approach. And we're now coming out and starting to talk to customers about commercialization. It's a team that's quite different to other quantum teams. We're a team that, yes, has the quantum science background and the quantum science credentials, but we've also been involved in the semiconductor industry for many decades. We've done products. Our CTO has been involved in the AI accelerator that's on Meteor Lake. Our founder, Dirk, led the team that did the first smartphone chips that integrated on CMOS. So we have seen silicon time and time again win out, and we've developed products that have been extremely deep tech and sold in the billions. And so we think that combination of technology commercialization along with the quantum science is what's needed for this next phase of quantum. So in summary, we see that there's a massive amount of momentum building for this approach. Spin qubits is really the foundational building block. There's now proof that we have the starting point, that we can start to scale these and start to think about demonstrating error correction in qubit arrays in the next 18 months. We take that and then we build a quantum system on chip around it with ARM cores, neural networks to leverage the best of classical compute. And then that enables a form factor that enables us to put data center ready rack mounted quantum computers into our customers' premises as soon as early 2025. Thank you very much.